everyone. The numbers are extremely dwindled today. We've got, let's see, I can literally count it. 6 people. We've got 6 people here today in person in a lecture hall built for, I don't know, 300 people or I don't know, something like that. Pretty amusing, which is fine. Hopefully most of the people then are watching this either live on Twitch or after the fact on YouTube, or otherwise, good luck, I guess. Okay, let's jump into it. Before we jump in though, does anyone have any questions about anything? Nope, no questions. All right. Well, updates, I guess, on course logistics. Still working on getting the reverse engineering survey out. I've been busy with other things. Finally, I think this afternoon I'm going to be able to get to creating it. It's actually, I've realized, so I've been creating all these like 5 multiple choice questions, and maybe, you know, that doesn't sound like anything to you, but it turns out like it's actually difficult coming up with good multiple choice questions just in general, where there's not like an obvious answer unless you know, understand the stuff. It's actually extra difficult to create reverse engineering multiple choice questions because hopefully the questions in the end, I don't know, I haven't created them yet. That's what's going to happen this afternoon. I can't really ask you questions about CImage because CImage is not the point. The point is reverse engineering, and that's like a very experiential task. I don't know. I'll come up with 5 fun multiple choice questions, but that has been the biggest blocker. I'll get to it this afternoon. There have been people that have requested extensions for various reasons, whether it's, you know, being sick or personal stuff or whatever. I think I'm behind on the order of 1 to 2 weeks or something like that. Hopefully going to process those this afternoon as well. And then I know we're missing survey extra credit, CTF extra credit, meme extra credit, and helpfulness extra credit. And also somewhere in this afternoon, hopefully that will also be processed. Otherwise, as soon as I possibly can. Okay, so that is course logistics. As everyone hopefully knows, we have our 9th assignment live right now. It is binary exploitation. It is due, or the checkpoint is due on Sunday. The deadline is a Sunday after that. Hopefully everyone understands that format by now. And then there will be one final module after it that's putting it all together, lots of concepts, all intermixed in very exciting ways. Hopefully people that have started on binary exploitation would agree that this module, is this thing following me? No, it's not. Hopefully people would agree that binary exploitation is a bit easier than reverse engineering. Do people agree with that or disagree? Agree? Raise your hand. Only one person agrees. All right, maybe binary exploitation, if you're at home, is harder, or maybe people are waiting for Sunday to start. Either way, hopefully you'll agree in the end that binary exploitation, I think maybe on the order of 2 times easier. You know, maybe this is like a web security slash, I don't know, what else have we done in this course? Web security, intercepting communication. It's not gonna be as easy as access control. You know, it's an average module. It's not gonna be like crypto or reversing. Hopefully you'll agree. Fortunately, this is not a brand new module on our end, so we've seen people hit pain points and smoothed it out, and you get to enjoy those improvements. And, you know, next, as Jan said last class, next semester students will get to enjoy your suffering of reverse engineering as we figure out how to improve reverse engineering. Okay, anyways, let's jump into conceptual stuff. I'm just going to start up a random challenge. So I guess I should make sure in the Twitch chat if there is any issues. Oh, people in Twitch chat say definitely a lot easier than Ari. Okay, that's it. No issues though. The audio is working. The stream is showing. Okay, cool. So yeah, let's jump in. Okay, so let's do a quick recap of what the heck is memory corruption, right? This is one of the primary topics in this module. Hopefully you've watched the videos If not, we will get people caught up to speed real fast with a quick sample program. We'll do test.c, maybe. What the heck is in here? What did Jan do to this poor thing? Okay, we'll go to temp. I don't care. Emexecute test.c. And we will write a nice little program. And this program will have one other function. It will be foo. And foo will have a buffer that is size 16. Now, what we're going to do is we're going to keep it real simple. We're just going to call stir copy. We're going to stir copy buffer hello world. Okay. So we're all on the same page here. This is a very boring program, but this is a introductory level C program, right? We got a buffer. We randomly decide to copy hello world into this buffer. There's really no effect of this. But what we can do is now use GCC to compile it. We will call this thing test.c. Oops. What? Oh, we don't know how to type. GCC. This, it complains about stir copy. We'll just, I guess we'll be correct for it. I am just not typing correctly. Test. Okay, we'll give it its include. GCC, test, nothing happens, of course. But what we can do now is we can watch this happen in GDB. And in fact, I'm going to set this to okay. gdb./test, and we can start the program. We can set it up so that we do set disassembly flavor Intel. We can set ourselves up where we will constantly see the next 8 instructions. I feel like that's kind of a nice thing to have going. What else do we want? I don't know. We don't really care about anything else. Let's just continue. Oh, no, we didn't set a breakpoint. So continue is a bad idea. Let's do start instead of start I. So the difference between start and start I, if you haven't caught on, haven't used GDB a whole lot, start I starts at _start, start starts at main. So that's the difference here. Sometimes you don't have a program with main, so start breaking on main doesn't mean anything because it's not a C program and there is no main. But for our cases, right, we got a nice simple C program with a main with the symbol for main there, so we get our breakpoint. Okay, now let's break on foo. Let's continue. We can see this is foo, right? These 8 instructions. I guessed 8. 8 was a good number. If we didn't know that it was 8, though, we could do disassess foo, D-I-S-A-S foo, and see the entirety of it. So we can see, right, that we have our function prologue here, which is we've got this RBP register. We are bound contractually to save RBP because we might mess with RBP, and you'll see very quickly that we move RSP into RBP. So we got to save RBP. We save it, we push it on the stack. You'll see at the very end, the epilogue of the function does a pop RBP. So this is the prologue, epilogue. And then we give ourselves some, we move RSP into RBP. This is kind of just part of shifting the stack frame. And then we do this. And in fact, we can see stir copy didn't actually, it optimized for us. We didn't even tell GCC to optimize at all. I guess this optimization just happens automatically. Like maybe stir copy is pound defined to do this operation probably rather than do the call unless it's some length or something like that. And we can see that we grab an address at RBP minus hex 10. This is our buffer pointer, our buffer that was size 16. That is at location RBP minus hex 10. That is the first byte. If we want to see the entire contents of our buffer, we could do x/16bx RBP minus 0x10. And here's the current contents of our buffer. You'll see that in our buffer, there is stuff, right? It's not 0 initialized. We didn't initialize our buffer to 0. C does not 0 initialize things. Often, the most likely byte that's going to be hanging around in memory happens to be a null byte. So often you might accidentally have a bunch of null bytes there, but unless you explicitly zero out your buffer, it is just a bunch of uninitialized data. And this is the uninitialized data that is right here. So we have that pointer. Then we take these 8 bytes, we put that into RDX, then we take RDX, move it into keyword pointer RAX. RAX is our pointer. So we moved 8 bytes into here. And then we take another 8 bytes, we move that into RCX, we take RCX, and we go to offset RAX plus hex 6 and dump that into memory as well. I guess, does that mean that this was only, how many bytes is this? 2, 3, 4, 5. I think this is 8. Let's just watch, I guess. This is the simple way to do this. So we can add display 16bx to RBP minus hex 10. Now we get to see the contents of our buffer every time we step. So we're going to step an instruction. Nothing very exciting has happened yet. We haven't updated our buffer. We know that updates to our buffer will only happen here and here after these execute. We step again. And then after we step on this guy, we should see 8 bytes filled into memory. Let's see that. We can see 8 bytes just filled into memory. Before it was a bunch of nulls. And now it is a bunch of stuff that got moved into memory. In fact, we could do x/s RBP minus hex 10 to view it as a string. And we would see hello, comma, w, and then this uninitialized junk that's in here. x/s is just going to go until we hit a null byte. Now we grab some more data, we put that into RCX, and we get ready to move RCX into RAX plus hex 6. Kind of a little bit confused. How the heck is it? Well, let's see. What is RAX pointed to? It is here. Well, let's see what happens. 6548. Before we had this plus 6. How did that just work? So we had this number here that we wanted to move in. So we wanted to move in, well, that goes here, 21, and then 64, and then 6C, then 7-2, and then 6F, and then 5720. Was it already 5720? This might just be some weird thing that GCC did. Yeah, look at this. 5720, and it also put 5720 here. Like put the constant into both instructions and then went to plus 6. I have no idea why GCC did this. Like why I was confused in my head is I would have expected RAX plus hex 8 to be the next location because we wrote 8 bytes. Then in theory, we're going to get ready to write another 8 bytes. Oh, you know what it is? It had to do this because when we move this, like when we do this operation, we're always moving 8 bytes. And we're not moving 16 bytes total, we're moving 14 bytes total. And so if it hadn't put this duplicated, let's see here, this 5720 and 5720, if it hadn't duplicated those bytes, those would just be like, what, null bytes or something? And then you'd be writing null bytes. But the behavior of stir copy isn't to add a bunch of extraneous null bytes to the end. You can add 1 null byte to the end. In fact, you have to. That's how stir copy works. But it can't add like 3 null bytes to the end. And so I guess this is how GCC resolved this, is it did duplicate within those 8 bytes and then did an overlap. Kind of crazy, but hopefully we can see now, for example, very easily that if we do x/s RBP minus hex 10, we can see our hello world is definitely in there. Okay, now this of course was not a buffer overflow, right? We wrote 14 bytes into a 16-byte buffer, not a buffer overflow. If we had written 17 bytes in, or actually even if we had written 16 because of the trailing null byte, that would be a buffer overflow. But we did not do that. And so nothing kind of disastrous happens here. So let's go ahead then and make something disastrous happen. We will do hello world, and this was 14 bytes, I think we decided. And then we will do 15, 16, and then 1, 2, 3, 4, 5, 6, 7, 8. So I'm just filling in the rest of the 16 and then randomly doing another 8 Bs, just kind of because 8 is a nice number. And then just always remember in this context, in the challenges, you won't really see us using star copies, I don't think. But in this case, there would be an extra null byte at the end that is also getting transferred into the buffer. Okay, let's GCC this as well. In fact, you can see that GCC has gotten a little bit smarter over the years. It's actually telling us that this dangerous thing is about to happen, that we're about to write more than 16 bytes to our buffer, but it's just a warning. You can continue on. And there are certainly ways to cause a buffer overflow where your compiler will not warn you that this is going to happen. Okay, gdb /test. Let's break on foo. Let's run. Set disassembly flavor Intel x16, or let's do disassess foo. We want to constantly see this, and then actually let's do 24 bytes. Even though our buffer is only 16 bytes, let's show the next 8 bytes after as well. Do that as a display. And then we also want our IP. Okay, so now we can always see our buffer and we can see the next to execute instruction. We can see it puts this into RDX, this into RCX, moves RDX in there, RCX in there. Here's our 8 Bs, goes into RSI, RSI goes in here, and we filled in memory. Any questions so far about like everything we've talked about? Hopefully this, you've written C in the past. You've looked at assembly for a few weeks now. Hopefully this operation makes sense, right? This is our stir copy. So now what is it that happens? Well, what happens is if I step and then step again, I did not do display 8i, display 8i, and we keep stepping, 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 and then x/s rbp minus hex 10. We can see we've got hello world, exclamation point, a b b b b b b. So buffer overflow definitely just happened here because the length of this string is too long. It is more than 16. Not good. I think, can we do call stir length rbp minus hex 10? Will that work? Is it just like, we're not going to worry about it. Somehow we could do that, or we could just copy it, however you want it to do. But okay, so let's see what's about to happen though. There's more going on here in this function. We had a buffer overflow. Does anything matter? Well, so far nothing matters. We're about to pop RBP. So we can look at what is going to get popped into RBP. That's going to be at the top of the stack. So these B characters here, right? B, 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 B. Looks like we had a null byte at the end also. This is about to become RBP. So we did just do a buffer overflow, and we're about to affect things. Because when we started this program up, we had an important bit of data that was here in our uninitialized data. This uninitialized data was in fact not really, it's uninitialized from the perspective of the buffer. Is not really uninitialized from the perspective of the stack frame. This location in memory was holding our saved RBP. So we wrote B's over our saved RBP. And so now this value here that's like 7F, FF, FF, this thing is an address right here. I can't really show it anymore, but we just overwrote this address here. And in fact, this is a stack address that was living here. And now that stack address that's going to go back into RBP is gone, right? Now there's a bunch of B characters. So if I step again, now we're going to do a ret. So we can see, and in fact, you can see my display function broke because my display function was printing x/24xb, and it was always just using whatever the current value of RBP was minus hex 10. RBP is an important register. And so now my GDB is kind of broken here for displaying this. it can't show me valid memory because now it's looking at all those B characters minus hex 10. Pretty interesting. And then we're going to do a ret. This is where, with buffer overflows and this memory corruption, understanding how everything works is critical. So the way that ret works is you can think of ret maybe in your head as a pop RIP, which maybe sounds like a really weird instruction to you, but this is equivalent to pop RIP. So we are going to update the instruction pointer with whatever is at the top of the stack. So what is at the top of the stack? Well, currently it is here. And if we look at 8 instructions there, we can see that this is like the end of main. We move 0 into EAX, we pop RBP, and we ret, right? This is main finishing out to do its return 0. So what is at the top of the stack is that location. This is how our program knows how to get back to main, is that this address just literally is sitting there on the stack saying, hey, when you're done, call ret and make sure our stack has been adjusted correctly. So when we do our pop RIP correctly with that ret, that we go back to where we came from. And call does the reverse. Call is like a push RIP. It's really a push. Well, yeah, it is push RIP. Looking at the next instruction that would have executed, it involves a push RIP followed by a jump to whatever it is that you were calling. That's kind of like a double instruction as a call. Ret is just pop RIP. So if we step, we can see we're back in main, back in main, back in main, back in main. Okay, let's edit this a little bit further then. So I think I was slightly off here. Let's see here. Just want to make sure I've got, yeah, see, there was an extra null byte in there because I was off by 1. So we'll put an A character in here as well. And then we've got our 8 Bs, which now we wouldn't have that null byte in there. And then let's do 8 Cs. 3, 4, 5, 6, 7, 8. Okay, GCC that, GDB that. We will break foo, display 8I RIP, and then we will do display. Hopefully it didn't move around. I don't see why it would have. Display 24, actually let's do 32 BX RBP minus hex 10, which hopefully is where our buffer will end up being once we hit our breakpoint. Let's do a run. Okay, now we are in foo. We forgot one thing here. Flavor Intel. Okay, let's start stepping. We can see it's going to put this. It's all going into memory, right? It's our stir copy all inlined. Let's do disassess foo. We can see this is our whole function that's going to execute. Let's start stepping. Okay, we are updating our memory. We haven't yet put these B characters and C characters in yet. We can see this right here and this right here. So let's actually look at this thing. So if I look at XGX right here, this is an address. And why is this an address? You'll get used to it in this module, but something that looks like 7F at the start right here, this is just very addressy. In fact, it's very stack addressy. If we wanted to confirm that for ourselves, we could do info proc mapping. And we will see somewhere in here, right in here, you'll see from here to here, this is the stack. So in fact, this is the stack. We'll also see that our code lives specifically in this RX permission page of memory. It lives from 401.0.0.0 to 402.0.0.0. So if you see something that looks like that, that is going to be code address E. So let's do, what do we want to do? So we can see here, we printed this address. This is a stack address, which makes sense. The RBP that we saved off, RBP is normally a stack sort of address. It's the base pointer of the stack frame. And then if we look at this guy right here, you'll see that it has a 40 lurking in here, which kind of spoiled that there. We will see, oops, didn't copy it correctly. If we look here, this is a code address. And if we look at 8 instructions right here, we will see, just as before, this is the end of main. So if we keep stepping, we're about to mess with those two things. We don't really care about our buffer, right? In this case, as an attacker, trying to maybe exploit this buffer overflow, of course, this is all just an example. We had a stir copy. There's no way for an attacker to even influence this program. But imagine it's a read, for example. This part of data we don't really care about. Just fill it with something. This, though, is is interesting. It's our saved base pointer. And this is really, really, really interesting, as we'll see here in a second. If we step and then step, and then so we just filled in all of the B characters. We step one more time. Now we filled in all of the C characters. Our saved RIP and saved RBP just got destroyed. Now we're going to step. Okay, RBP just got popped. We did pop RBP, and now our GDB is failing again as before. And the real interesting thing, though, now is this ret. And as I said, ret is just pop RIP. So if we look at XGX RSP, the top of the stack, we're going to pop this into RIP. This effectively means we're going to jump to this address. And hopefully it is no surprise. But when we go to do that, when we jump to this address, we get program received signal seg_v segmentation fault. You cannot jump to this address because this address is not mapped. If it was in here by chance, maybe there was this weird address located in our memory space that was just a bunch of C characters, then we wouldn't have crashed. We would have just started executing there, assuming it was an executable page of memory. But in this case, not so lucky. And so we crashed the program. We got a seg fault. And I think, let's see if GDB actually, no, GDB is not so smart. Yeah, it lost that. But what we could do, let's see here. If I run test, right, we get a segmentation fault even without GDB. Let's see here. Now, okay, so you'll see that a file just got added. It's this core. So when a program crashes, if your system is configured for producing core dumps when the program crashes, you'll get one of these core files. This core file can be loaded up into GDB, and you'll see the core was generated by /test. And now, you can see that our RIP is still there. I guess it doesn't update RIP at the point of crash. But if I look at the top of the stack, those C's are there. So we can see that we crashed on a ret instruction. Still at the top of the stack is RSP. And in this case, I didn't even need to use GDB, right? I just ran the program and it says segmentation fault core dumped. This is the core it's talking about. So I can just load that core into GDB. And actually, you have to do, as I did before, /test and then core. So the program and then the core dump associated with it. And I can just look at all of memory at the time that the program crashed. So this gives me a lot of interesting information, right? It tells me what instruction did I crash at. I can run a GDB command like BT, which is the backtrace. I guess our backtrace got kind of destroyed because it doesn't know that main called foo, because the way that backtrace works, it's looking at our call stack. The way you normally analyze to figure out your call stack is you look at the stack where all those saved RIPs are. And so, I guess our backtrace got destroyed. But now, even without GDB analysis, throughout the crash, we can look at a postmortem of the crash and see what the heck was going on. We were on a ret instruction, and always look at the top of the stack when you crash on a ret instruction. This is where we were trying to go. And I wonder, info proc mapping, I bet that works, yeah. And we could see, that is not mapped into memory. Okay, any questions so far at anything I've said? I'm gonna also pull up Twitch chat just in case. Okay, I'm demoing GDB a lot because GDB is like, if the stuff just makes sense to you, you could probably just fly by without GDB. But as soon as you're confused and things aren't making sense, GDB is going to be your tool. Okay, I don't see any questions in Twitch chat yet either. Okay, there's a lot of directions to go here. The first one I'm going to do, maybe you don't like this whole, set disassembly flavor Intel and display 8RI or 8I RIP and display 8BX, RBP minus hex 10 and constantly typing this over and over. Two options, or a few options, GDB init. Hopefully you've learned about GDB init because I think Jan has talked about it several times. You can do a GDB script. Hopefully you understand some idea of a GDB script because the GDB portion of Computing 101 went over that. Kind of a third and easiest alternative that maybe you'll see a lot of people doing, especially a lot of people that do this sort of analysis where they're sitting in GDB looking at this register. It's kind of like a lot, and GDB is like, defaults aren't so good. They're basic, they're fine, but there is an easier sort of nicer wrapper around GDB that makes a lot of this even easier. So let's see what that is. So there's two popular tools. One of them is GEF. So I could actually go GitHub GEF. These are just projects out there that a community of people have maintained. This is GEF, the GDB enhanced features. And then there's a second popular one called pwn.debug, which makes exploit development and reverse engineering with GDB, it's made easy. So these are two very popular tools. They're just wrappers around GDB. You can run them by just typing pwn.debug /test. Okay, now you will get some color. Maybe this color isn't so exciting. But what we can do now is we can start the program. And we get a whole lot of info dumped to us. And it's not very good because I'm zoomed all this way in. But if you're like on a big monitor and you've got space to work with, I'll zoom out a little bit just for showing this off a little bit more. Well, let's clear, debug, start. Yeah, you can see that it's kind of nice. We can see all of my registers. I can see what code is about to execute. I can see my stack. I can see my backtrace, that underscore start called into libc start main impl, which called into libc start main, which called into main. And I could break on foo. It's still just GDB. I can set breakpoints. I can continue. Now we can see that foo is in my stack trace, and it's kind of cool. We can see, for example, in my registers, we'll zoom in because I recognize streaming zoomed out is even worse. We can see, for example, that RAX is 0. We can see that RBX is this address, and this address actually points to this address, and at this address is this string of memory. So we have a pointer to a pointer which contains this data, right? So it kind of is very cool. We can see, RDX eventually, through a chain of pointers, makes its way to the shell environment variable. Yeah, so we can also see R9 ultimately is a code pointer, right? It's pointing at this dlfini function. We can see RIP, of course, is also a code pointer. It's pointing at the next to execute instruction. R15 is a code pointer. We can just kind of quickly see things without having to constantly type x/blah, blah, 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 blah. A lot of things you might just naturally wish I could see. It's already set up to be displayed for you. And it does color coding. I guess red is code. Yellow must be the stack. Maybe there's other colors out there too. I don't know. Maybe some of these are like ASCII versus non. No, I don't think that's what it is. I don't know. It is very cool though. And there's a lot of really advanced features that we won't even actually need in this class. But if you go on to Take 466, there's some advanced features in here that make just various tasks easier. There's like another tool to learn. You don't have to learn that pwn.debug. I mean, you can as you want. The crucial thing here really is just, you get all this stuff displayed to you for free. And every time I step, I can see what's going on. So for example, let's see here. RAX ends up becoming my buffer. So we can see that RAX is this guy right here. Let's watch what happens. It's very difficult doing this in a zoomed way. We can see that we're about to write to the buffer, which is pointed to by RAX. So we should see that this gets updated with a string because we know it's a string getting written here. Yeah, so you can see now that RAX points to hello, comma, space W. And if we step one more time, now, wait, what? Why did it not update? Step one more time. Oh, maybe it like constrains how much of this. No, but it shows more of the string there. I don't know. If you like it, feel free to use it. If you don't like it, don't use it. Just use vanilla GDB. One other thing I'll just quickly show off is GEF instead. Same idea, just a little bit different. If I start, you can see very similarly, we get colored stuff. And if I break on foo, we continue. You can see my upcoming executed instructions. We can see that if I step, 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 okay. I don't know why it doesn't give me the whole string, but whatever. Even this one doesn't. But either way, this is, two options that I figured I would point out now while you're, maybe about to be embarking on using GDB a lot, that these are two options that you might like. Okay, so that's what I'm going to point out there. So I'll see, is there any questions about that, pwn.debug or Jeff? You don't have to use them. It's just like fancier GDB with lots of features that you don't need to learn, but the default is also kind of nice. No questions. All right. And I don't see any questions in Twitch chat, so we will keep on moving. Okay. So let's edit the code here. Let's make this a little bit more interesting. So we've gotten this program to crash so far, right? By putting these C characters in here. I'm going to change up this program where to be a little more in line with how these challenges actually work so that I have control over what my buffer overflow is rather than just stir copying in a static string. I am going to read from standard in into buffer 4096 bytes. Okay. So that is that. And I'm going to add a fun little function here. Oops, not called main, called win, which you'll see that many of the challenges in this module have. Ours won't be as cool as reading the flag. Instead, we will just put U1 and leave it at that, because that is just as good as the flag, a nice U1 message. And then we will gcc test.c. We'll listen to our warnings, at least this one. I don't know why I choose to listen to some warnings but not others. I guess maybe because, wait, foo. Am I missing? Who gives me foo? Man to read. This guy gives me read. We'll fix that warning too. Is this just it figuring out that there's a buffer overflow? Yeah, this warning we're not going to fix because this is the whole point. It is warning us that there is a buffer overflow at play or potential for it. It's a warning. Okay, so if we launch up ./test, wait, what? Oh, I didn't do test. ./test, it hangs now. I can, and we'll zoom in a little bit more. Oops. I can say A, and it does that. As Jan showed famously, you just type a whole bunch of A's and programs crash. Now we know why the program crashed very directly, right? The saved instruction pointer got overwritten, and that is never good. But what if we want to do something cooler than segmentation fault core dumped? What if we want to win, for example, right? So we saw that there is no way to call win. But we also just said that we're in control of where foo goes to after this function executes. So you know what? There actually is a way to effectively call win. It's called return to win, right? Instead, we don't get to modify our source code, but we get to modify saved RIP, pop RIP, and effectively jump anywhere we want. A very cool place to jump would be to win. And then you would call this return to blah, return to win. Is kind of the name for this type of exploit. There's other very related things. There's like ret to libc. So you might return to a libc function. We're not going to really get into that right now, but libc might have somewhere very cool for you to jump to. Anyways, let's go ahead and ret to win first. So before we can do that, I feel like we kind of maybe, hopefully, if you've been paying attention, you have kind of a good idea of what we're going to do. We're going to send it something like 16 A's to fill up this buffer, which there's definitely 16 bytes of space sitting in there. And then there's like some distance until we reach the saved instruction pointer. Before, there was like another 8 bytes, which was the saved RBP. We didn't really care about saved RBP. It's still, we could influence the saved instruction pointer and return somewhere. But either way, there's those 8 bytes we have to deal with. So we have 16 bytes, then another 8 bytes. And then at least if it's going to look the same as before, if GCC didn't like change stuff up and add padding or do something weird, then in theory, the next 8 bytes would be our saved instruction pointer sitting on the stack that what this implicit return at the end of this function will go to. Here's where we would use IDA, or I think it's going to be okay if you want to use objdump here. Objdump is nice and simple. In this case, I would say objdump is going to be a quick way to look at this. Let's look at foo. We can see that we push RBP. So the thing to think about in your head, when foo is starting, the very top of the stack, as soon as before this instruction even executes, at the top of the stack right now is the saved instruction pointer, because someone called us. The saved instruction pointer is at the top of the stack. We push RBP. Now the saved instruction pointer is 8 bytes away, okay, from from RSP. Then we sub RSP hex 10. So what this did, it didn't do anything that fancy, except it allocated 16 bytes of space on the stack for us. This is, if you've used malloc on the heap, for example, to give yourself 16 bytes of memory, this is the local variable stack equivalent of malloc. It's literally just, give yourself some space on the stack, sub RSP hex 10. And then, well, this is, maybe a little less intuitive. Here's like kind of a little bit of an issue, is that we're working with RSP and RBP, which means our math isn't so simple. But at this point right here, we actually put RSP into RBP. So we can kind of ignore this instruction to some extent, right? RBP minus hex 10, right here at this point, RSP is 8 bytes away, and then we subtract a further 16, so we're 24 bytes away. Maybe that's like, gymnastics of reasoning about this and doing math, and like this goes into this and like subtract this. Maybe you don't want to do that, which is, fair, but that's kind of how you could do this static analysis. A different option, actually, I'm going to see, this one's kind of cheating. You don't actually have this option. I think if I compile it like this, it won't use RBP. Let's see. Foo. Yeah. And you'll see we also don't even save the base pointer. This just compiled the program optimized for space, which means a bunch of constants that can get like folded together, Turned out that we didn't actually need to save the base pointer if we just never mess with the base pointer. Kind of a nice little saving of space. And so all we do right here is we just sub RSP hex 18, and then ultimately we call into read add RSP 18, and we can see right here that at this point, right, this is probably easier to look at. In fact, maybe we'll recompile these challenges with OS because it might even be a little bit easier to think about. We'll decide on that. But you can see here that we subtract 18 from RSP. At RSP before this subtract is where the saved instruction pointer is. This is going in to be our buffer to read, our second argument. The saved instruction pointer is hex 18 bytes away. This is like very easy to look at. But of course, unless we recompile things, you can't do that. So we won't consider that analysis. One final thing we can do to not have to do math, and this is probably my general favorite way to do it, is nice simple GDB or pwn debugger Jeff /test break foo run set disassembly flavor intel disassess foo. Okay, right here we've got xgx rsp. So I guess when you break foo, it actually breaks past these two guys. So that's kind of lame. But at rsp plus 8, this guy right here. So at rsp is our saved base pointer that happened here when we pushed rbp. At rsp plus 8, we've got this guy. So this address right here, this blue guy, the 7FFFFE318, this guy is where our saved instruction pointer is. Now all we need to do is break at read. So we will break here. And we know that at this point, actually we got to continue. At this point, we're about to read. And what that means is RSI contains the location where we're going to read to. RSI, okay? And we already figured out where our saved instruction pointer is. So if we just print this minus this, 18, it's 18 bytes away. This is my preferred, it's like you can't mess this up, okay? This is where data is coming in. It's at the read. It's coming into the location specified by RSI. Just print out where that is, and then also print out where the saved instruction pointer is at the start of the stack. Subtract the two. You don't have to statically analyze and read IDA or read objdump or like do subtraction. I guess you have to do one thing of subtraction, but just very directly, where is your first byte of data going to go to? And where is the first byte of the saved instruction pointer? That difference, hex 18, we need to fill in hex 18 bytes, and then the next bytes is the saved instruction pointer. Highly encourage you to do it this way. It's like foolproof. You can't mess this up. Reading this and trying to do math, you can mess this up. You can always recover with GDB, but that is going to be my tip for you all. Okay, so then now what? Well, we need to figure out where we want to go to. So before we were just returning to a bunch of C's. Let's grab objdump or IDA or whatever. Really all we want to know right now is where the heck is win. Win is right here, this address right here. If we redirect RIP to this location, suddenly we are going to start executing push RBP, then this, then this, then this. You might be thinking to yourself, and it's a good thought, but what about that saved RBP? We like messed with RBP and now RBP is all destroyed. And if someone look at this, people might start using RBP and like, how is this code gonna function? We've already messed things up. Well, don't worry, because Win is very nice, like every function in this program. It immediately just saves off RBP and then clobbers it with its own thing. So the fact that you destroyed RBP, it actually doesn't matter at all, because the first thing Win does is gets rid of it. It just saves it off, even though it's a broken bad value, it saves it off and replaces it with a good value. So not an issue there. So we just need to go here. It's very simple, right? 18 bytes, that address. Now the question is like, how do we properly format it? Here's how you properly format it. Hex 18 bytes of padding, okay? And then, well, we have a couple of options. We're just gonna immediately go to the simple one. Let's not even mess around. How do we type that? How do we correctly do this, right? This address right here, don't forget your 0x. This thing right here, right? I can't do BA times hex 18 plus this. Python will tell you, nope. You can't do this. that's the same thing, right? Can't do that. If you do this, very silly, don't do that. This is also completely incorrect, right? This is like you're putting ASCII bytes in here. This is not, you're trying to get this 64-bit little endian integer into your payload, right? 18 bytes here, this should be 8 bytes. And we can very clearly see that this is way more than 8 bytes. The way that you do it, very simply, is you import pwn. This is pwn tools. Maybe you've used it so far in this class. And you do p64 of this thing. And what this does is it gives you your 8 bytes correctly put into as a little endian integer, right? This looks like nonsense. Looks like nonsense. That's good because it should look like nonsense, right? The very first one should be whatever the heck 36 is. Wait, what? Oh, hex 36 is, which is a 6, right? And then this 1, 1 here, remember we're doing a little endian integer. Well, there's our x11. And we've got a 40 in here. There's our at. And then the rest is null bytes. So there it is. Very nice. Don't even have to think about it. And so what we can do is import pwn ba times hex 18 plus pwn p64 of the address of win. Okay, very cool. There is our payload. Now, how do we get the payload into the program? We could, of course, open payload for writing as bytes, write this thing out. Now I've got a payload that is my data, and then I could do /test payload, right? And this will work. You won. So we successfully diverted control flow. Now, it wasn't clean, right? The program crashes after. And in fact, we could see why it crashes after. We get a core dump now, /test core. What happened here? Well, RIP is 1, so that's not good. Probably our backtrace is gone. I don't know, bad things happened. We actually can't so easily see what happened because our RIP got destroyed. We have some state we could run the payload and step through and set breakpoints and like watch this destruction happen at the end. In fact, let's actually just because we're going to really hammer in the importance of GDB here, we will do that. We're going to run with payload. We're going to start with payload. We're going to break at foo. We're going to break at win. We're going to set disassembly flavor intel. And then we're going to continue. We're in foo. We don't need to watch foo happen. We know that we hit win. Let's do display 8i RIP. Let's watch what's going to happen here. So we step, or we next instruction, I should say. We skip over puts. There's our U1, nop, pop RBP. This isn't going to crash us. That's fine. Okay, what is at the top of the stack now, right? We've messed with the stack in weird ways. What is here is, oops, we just want one word. Well, there's a 1 there. Why is there a 1 there? I don't know. Your exploit did some weird things, and that is just what happened. Yeah, so yeah, we're not going to figure out why there's a 1 there because we don't really care right now. If you're interested in answering that sort of question, maybe we'll get to it. Or if you're really interested in that question, 466 might be the class for you. There is a very interesting thing with this ret that happens now at win that is a very real way that people exploit software that, you know, it's not just one ret. You want the next ret, and then the next ret, and the next ret. And it turns out there's this whole, I guess I'm spoiling it, thing called return-oriented programming, where you can ret to ret to ret to ret. You have all these small little snippets of code that execute, and you come together like Legos because no real program has a function called win, but it does have all these Lego blocks of code, and you stitch them all together with a bunch of rets. It's called return-oriented programming. There's the spoiler there. If you're interested in that, take 466. Okay. There was one more thing I was going to show, though, because this is actually super lame. that we just create a payload file. No one in their right mind would do this, I guess, unless you only halfway know Pwn tools and you want to use GDB, but there's an even better way to use GDB with Pwn tools, so you would still be a little bit crazy for doing that. We will say that this is our payload, and we would say with pwn.process./test, this starts up a process object, and then we can write our payload to it, and then we can print process.read all capital S to convert it from bytes to a string so that I can nicely print my U1 message, and we will see a U1 come out at the end. And we'll also see, did I lose my, yeah, we'll also see that process.pull, which gives me the exit code of my process, was a -11, and -11 is seg fault. I guess you'll see it's +11 here, but just take my word for it. 11 is a seg fault. Program crashed with a seg fault. I think we could also actually do process.wait at the end. I don't know. I feel like there's another way to get it to show that it's seg faulted, but good enough. Okay, I will once again ask any questions so far. And I guess I'll open up Twitch chat to see if there's brand new questions. All right, cool. All right, let's show some more fun things that we can do with Pwn tools. Okay, so which one do I want to show first? Okay, here is a fun thing that you can do in Pwn tools. So before we used objdump to figure out the location of win, Pwn tools can do that. So if I do elf of test, pwn.elf of test. Now we have this elf object that it looks like Pwn tools automatically analyzed to determine that it's an AMD 64, aka x86 64, a little endian architecture with this thing called relrow, which is set to partial relrow, and this thing called stack canary. There's no canary found, and this thing called NX. It's enabled. These things don't necessarily immediately matter to you, but all of these things actually, these three, I think get covered within this module. I guess technically we don't talk about NX. NX is the idea of whether or not the stack is executable. Or I guess more generically, if any page of memory is both writable and executable. But I think probably this, in this case, is just talking about the stack. I don't know if it's analyzing more broadly. You could think about the case, and in fact you will at the end of this module, think about the case where there's no win function. But if you're in a situation where the stack is both writable, as in memory there can be modified, and executable, you can just write your own win function and then jump to that thing. So this is the idea of NX. In general, you should never have a page of memory that is both writable and executable. Like, why would you ever want data that can be modified and interpreted as code at the same time? Generally speaking, you never want that. Except there are exceptions to that. First of all, older hardware just made all memory readable, writable, and executable. So there just wasn't hardware to facilitate this idea of different permissions on the memory. Now, of course, modern hardware supports whether that memory is readable, writable, executable, or some combination of them. And then there is a more interesting reason that this exists, and that is a just-in-time compilation. So there are programs like, for example, your browser, your JavaScript that's running. As it's running, decides at some point, as it's interpreting, right? It's just like Python, JavaScript, they're just interpreted languages. It's interpreting. At some point, the engine decides that this code is being executed a lot. It's being interpreted a lot. And it just plays this game where it takes the logic of that, it analyzes it, and it just converts it into x86 64 and says, okay, now I don't need to do this interpret over here. Next time I want to execute this logic, just jump there and then jump back in to the engine. And so in that case, you want to both write out x86. Like you're compiling on the fly, you're writing, and then you also want to execute it. And then there's a whole security game of like, yeah, I mean, there's an obvious thought there of why does it need to be both writable and executable at the same time? And it doesn't, right? You could just make the memory writable and then make it not writable, but then make it executable. And then it's never writable and executable at the same time, which is very good. Except JavaScript, for example, is doing this all the time. And there's some performance overhead to changing the permission of the memory. And so they just said, screw it, we're just going to leave it always writable and executable, and now I don't have to pay that overhead. And people like to not pay overhead because just don't have a buffer overflow or memory corruption, and then no one can abuse this anyways. So that is the performance game. And then, I think I've heard recent things about there's some hardware thing that allows different perspectives on the memory, where from one perspective it's writable and in another perspective it's, I don't know, the security is a cat and mouse game. That's NX. And we will look at pi and stack throughout this. Okay, anyways, we've got this elf thing. If I want to get the address of win, wait, what is this thing? I don't even know what that is. Oh, I guess that's where probably underscore start is. Funcs. I could read the documentation. Functions, here we go. Win, address, hex. Look at this. Now we can make a real fun way of doing this. Elf functions win address. Now we can put win adder here. And now it still wins, and we didn't have to have this random magic hard-coded value. There is pwn.pack. How does this one work? No, that's not what I want. Pwn, pwn. All right, the next one I was going to go over, it doesn't really matter. There's a way somehow to specify that at offset 18, I want this thing right here, and then it'll just automatically fill it in with other bytes. But who really cares? Just do this. This is fine. Okay, one more thing, though, that I will show off is this. Let's say that you're writing your payload and you did this, right? You didn't even realize it, but you put a 7 there instead of an 8. And you're like, my exploit is not working. And you're like, but what happened here? Whoops, not waits, pull. Well, it did seg fault. Something went wrong. And you're like, what the heck is going on? I need to use GDB. But like, what, do I need to now take my payload, write it to a file, run it through GDB? No, let's just pwn GDB attached to the process. And you're going to see that that fails, right? So it was almost cool, but it says could not find a terminal binary to use. If I launch this up in tmux instead, it will now work. So now at the top, I've got my IPython. The bottom, I've got GDB. So this is a pretty cool way of doing this. And now I can set up or I guess I can see, where am I right now? I'm currently in read. And if I look at my backtrace, I'm currently waiting in time at this read function because it attached and then it sent the data, but when it attached, it did a break. So it attached and did a breakpoint, and it's paused right there. And pwn.tools has technically already sent the data, but GDB in the process won't continue until I tell the debugger to continue. So we're like frozen in time at this read. So what that means is that I could set disassembly flavor Intel, and I could look. So I did a backtrace. So foo was calling in here. Actually, backtrace. If I go up the backtrace, Now we can see right after the call is finished, I will go to here and then here. Maybe I decide like, you know, generally speaking, when you're crashing the program, but you're not like winning, the thing you want to do is watch the ret happen. Because if you're crashing the program and you're not winning, or you're like your win code's not executing, it means that you definitely overflowed the save instruction pointer, or probably, technically there's other ways it could crash. But you may have overflowed the save instruction pointer, but overflowed it with the wrong value. So what I would do here in this case to figure out what's going on is I would break at this ret, because this is the ret that I'm trying to mess with. And then I would continue. And now I can see that the thing I'm about to execute is this ret. And so if I look at the top of the stack, and you know, maybe as you train your eye a little bit more, you'll see like, oh, it is a 40 thing. That sounds like a code address, but it's shifted off, right? It's definitely not 4011, right? It's supposed to be one more over. So this just immediately tells me, and in fact, maybe your eye isn't trained. You can second guess that as well. What you can do is you can say, all right, what are the instructions right here? I better see my win function instructions right here. And it'll say, no, you cannot see that. But what I could do is print the address of what? Well, I could do x8i win for sure and see, right? So the issue is now we're in tmux, and that means if you want to really use this, you got to figure out tmux a little bit. If I want to scroll up, I can't just scroll up because tmux like just has this portion of my screen, and now I'm scrolling like outside of tmux almost. But if I hit Control B, left square brace, you'll see that now there's this yellow thing over here which says 0 out of 86. Wait, what? Well, I must be able to do, oh, I can up arrow for sure. And you can see here, right, that I had 4011, and this is clearly, we're missing a 3-6 in there. So the answer to this is, right, we're off by 1. Hopefully you'll be able to jump to that conclusion that you're off by 1. I could have gone the other direction. In fact, before I go the other direction, let me show one more thing, you know, this bag of tricks lecture stream. There is a way to make it so that tmux is way easier to use. Pwn.college tmux conf. This thing, just like a GDB init, has a tmux configuration file that just does one thing, and it makes it so that the mouse works. I am going to copy this thing into my home directory. And now tmux will work a lot better. So we're going to do this. We're going to do this, this, backtrace, set disassembly flavor Intel X8i, or let's disassemble foo. We wanted to break right here, and then continue and print the top of the stack, which is off by 1. But now I can like click between, and I can also scroll. My like trackpad is working. So that if you want GDB to be more usable, take that tmux configuration, rewatch the stream and go to that frame or whatever. It's not so difficult. It's just like set-g mouse on in your tmux.conf. And now we can use this and this, and it is very cool. You might also prefer instead, like that you don't like that it's like, this feels very scary or something, like in terms of timing things, right? I'm attaching and then I'm immediately writing. I can make it so we don't immediately write. I can say pwn.pause, and now I haven't actually sent the data. I can continue now in GDB, and you'll see GDB is still hanging because pwn.tools is paused. And paused is just read 1 byte. It's just waiting for you to say enter, and then if I hit enter, the data sends and I get my seg fault. So that is another cool thing you might like. Any more questions before we're running out of time quickly as I try and show you tips and tricks for getting yourself unstuck on these challenges? The entire game is going to be GDB. Either you know how to solve it in one shot, or you make a mistake, almost guaranteed, and you use GDB to fix your mistake. Okay, no questions. Okay, is there anything else that's worth showing in the next 4 minutes that I'm missing? There's a whole bunch of other really cool things in Pwn Tools. So for example, later on in the module, we'll show this part. Later on in the module, my hesitation is that some of these things in Pwn Tools just make things too easy. So like my solution to that is to just not show it to you, because otherwise it's too easy. We'll show you this one though. I think maybe you've already seen this, in fact. Pwn.asm, first I need to say that my arch is AMD 64, and then I can do like move RAX 42, move RBP 33, NOP syscall, right? Something like this. And it will emit the raw bytes for that. Later on in this module, there will be shell coding, and you might be like used to running the assembler and like obj copy or like weird ways of getting the bytes out. If you're already using Pwn tools for interacting with these challenges, you'll probably just want to use pwn.asm, because guess what? Now, if I have my payload, right, I might have like a payload equals this, and this payload doesn't really make any sense, but hopefully you'll see where I'm going with this. You might do something weird like this, right, where this weird payload that is a bunch of A's and then a win address and then a bunch of assembly, right? You're crafting this complex payload. And so if you're already using Pwn tools, rather than like switching tools and then switching back in, pwn.asm if you need to emit some bytes of shellcode, very nice. Also, real quick, pwn.disasm does the reverse. So it takes the bytes and shows you what the heck you just had. Okay, I think that is all I will show for now. Good luck on the module.